Hi, in this video, we are going to talk about how the forwarding works in the NCS 5500 platform. We are fairly familiar with the routing protocols such as OSPF, ISIS and BGP. We know how a router typically learns and shares their network information. In this video, we are going to look into the internal resources of the router. We will see how the router stores this routing information and how they all come together during a forwarding operation. Let's get started. So before we deep dive into the internal resources of the NCS 5500, let us understand the basic principles of forwarding. For a simple IP routing case, a router needs three pieces of information. The first thing is the adjacency router or the next hops that the router will learn via basic protocols such as neighbor discovery or ARP. It can also be statically configured. The next step is understanding the ecosystem through the routing protocols such as ISIS, OSPF or BGP, and we may also direct the router with some static routes towards a specific destination. And the third important piece in the puzzle is connecting all these destination prefixes learned from the routing protocol and the next hop or the adjacency that we have, and determining which specific destination can be reached via which specific adjacency. And in some cases, we may have multiple forwarding paths, also known as the equal cost multipath or ECMP, in which case we may have some additional set of information that needs to be stored in the router. Let us now look into a simple IP routing case and see how all these are set up internally within the router. For our demo today, we have a simple 4-router topology. The routers R1 and R3 are the spine, and R2 and R4 are the leaf nodes respectively. The leaf node R4 is a NCS 5500 platform running Jericho Plus ASIC and XR731 code. The R4 node has one uplink each to the R1 and R3 spine. All the routers in this topology run IGP protocol and distribute their loopback to each other. As you can see, at the R4 node, it has an ECMP path to node R2, the loopback 1.1.1.2, and a single preferred path towards the node R1 that's depicted by loopback 1.1.1.1. We will now start following these two prefixes 1.1.1.1 and 1.1.1.2, which is the ECMP, and see how the forwarding is programmed in each of these cases. On our forwarding chain journey, the first stop is the prefix lookup. Typically, all the IP prefixes, MAC addresses, and the MPLS labels can be stored in the LEM, LPM, and in the scaled version of NCS 5500, they can also be stored in the ETCAM. We have a separate detailed video on where these specific prefixes based on their length and the address family are stored, and I have left that in the description below. Moving on, let's see in this specific case where our prefixes are stored, that is the 1.1.1 and the 1.1.2, and we will see what are the details that we can gather from the first lookup. So for our case, we are first looking into the forwarding information at the LDM table. In this list, pay attention to the entries 21 and 22 for the IPs 1.1.1.1 and 1.1.1.2 respectively. You can see in the payload that it has a pointer to the next entry in the next table that we need to use in the forwarding chain. For instance, for the 1.1.1.1 entry, this is pointing to the FEC table ending with FFC7. But in case of 1.1.1.2, which has an ECMP path, there is a different entry that is ending with 0001. And this is actually an entry within the ECMP FEC table that we will see next, that will further point to the array of paths that is in the FEC table. After the first lookup at the LEM table, we now have the pointer towards the FEC table with the specific entries for either the FEC for the single path or for an ECMP FEC table entry. The ECMP or the equal cost multipath FEC is nothing but the first 4000 entries within the FEC table itself. These are just a reserved port of entries that are going to be used in case of a ECMP scenario, and this is nothing but just a pointer to an array of FEC entries that is further going to be looked upon. Now in this case, we will see first what is going to be there for the case of 1.1.1.2. What is the ECMP FEC going to look like, and what are all the specific information that we can gather. Now we are looking at the ECMP FEC table entry. Here we see two pieces of information. The first is a pointer to the FEC table entry, which is the first entry in the path list. Here it is FFC5. And the second one is the entry for the number of paths. In this case, since we have two ECMP paths, we see the size is 2. So essentially, our entries are going to be FFC5 and FFC6. Next, let's check the FEC table entry itself. First, let's check for the entry 1.1.1.1, which had a single path ending with FFC7. In the FEC table for this specific entry, you can see that we have two results. The first is a pointer to the encapsulation table ending with 0004, which determines what is going to be the outgoing label when we send this packet towards this destination. And the second is an entry to the egress interface itself, which is specifically pointing to which queue for the egress port this packet must be moved. We have a specific section and a separate video on the Vivo queue that will be added later, and I will leave the description below for this information on virtual output queuing on the NCS 5500. Next, we will look into the ECMP case. In the ECMP case, we have two entries as we have seen before, FFC5 and FFC6. For each of these FEC entries, there is an encapsulation and port ID. Note that the encapsulation 0004 and the 081E port number are common for both the prefixes. This implies this specific packet going to either destination will have the same encapsulation out of the same egress interface. This is uniquely possible on the IPv4 scenario, whereas when we talk about the labeled with the MPLS scenarios, we will see that out of the same egress interface, we may sometimes have different encapsulations. Let's quickly recap what we have seen so far. We have taken these prefixes 1.1.1.1 and 1.1.1.2. Now with these two specific prefixes, we have first looked up into the LEM table. We got the pointers to the FEC or ECMP FEC respectively. Further, we have looked into the FEC table itself, and there we saw again two pointers which are pointing to an encapsulation database, which is going to give us the final link layer encapsulation that we need to add to the packet, and it also points to the specific port or the egress interface out of which the packet needs to be moved. Note that all this lookup process has happened just on the ingress side, and this is one reason why we call this a single stage lookup platform, because all the specific major tasks of the lookups happens on the ingress itself. And on the egress side, let's see what are all the additional tasks that will be taken care of. Now, before we look into the encapsulation data itself, we need to understand how this data is stored in the egress side. Now, when a line card learns about its next hop or adjacency, it first learns that information and stores locally as a local entry, giving an ID which is locally significant. I mean locally because the ingress side could be in a different line card that may not be aware of this specific entry. So to make the entry available for all the ingress interfaces across all the line cards in the chassis, we create a global ID. Think of this as a sort of table that's maintained centrally on a route processor. Now this table is sort of assigning, or each time the line card learns about a new adjacency, it requests for a global ID and it shares this global ID to all the ingress line cards. Now you would have guessed that the specific information we got from the FEC table is actually the encapsulation global ID. So in the next steps, we will see how we map this global ID to the local ID on the line card or the egress side of the NPU. And from there, we will see how we identify the outgoing encapsulation. Now we are at the final hop of our forwarding journey. Here, let's look at the entry in the encapsulation data. Here you see the global ID, that's 1004, which is now translated to the local ID 4008. This is actually the global to local mapping that we were talking about. Think of this as a small table that's locally meeting on the line card to get a pointer to the local entry. Note that we also see the destination, there is the destination MAC. Recall this is the same MAC we learned in the art earlier. We will also now see the entries for the ECMP paths. Note again, for the ECMP path, as we have seen earlier, the second entry is actually pointing to the same interface that we have seen earlier, which means that the packet out of this interface will have the same encapsulation for either destination. And this is basically the link length encapsulation. Now here is a bonus step. If you want to see all this data in one place, you can do so using the showsef command, and this is also the recommended way. You could use the hardware egress detail option, and first we will look into the option for the 1.1.1, which has the single path. Here you see the next hop is the 10.0.0.0.8 interface, and under the hardware block you can actually notice that the leaf or the prefix entry is actually in the LEM table, and further you can also see that it has a single path and the entry that is available within the FEC encapsulation and also the destination MAC with the outgoing interface. Now let's also quickly check the ECMP case, that is 1.1.1.2. Here you can see that it has two next stops. Again, the prefixes are pointing to the LEM or the LEM table, which again has points to the two paths on the FEC table that we saw earlier. And these are pointing to the individual next stop info or the encapsulation details that we have recently seen. There are two ECMP paths programmed that you see in the bottom of the output, which are load distribution available for forwarding. So in this video, we have seen how a simple IP routing works on the NCS 5500 platform. Just use the showsef command that I have used in the end of the video if you want to look into all the resources in one place, because all the internal commands that I have used may change per release and I just want to save you the pain. Now, in the future videos, we will see more forwarding use cases such as MPLS, segment routing with V6, and also the layer 3, layer 2 services, where we will delve deep into how each of these services are constructed and the resources are aligned for the forwarding. Thank you.